right, here we go. Welcome to lesson 9.3 geometry notes on similar right triangles. We'll build on some stuff here. So similarity was the previous chapter. Chapter 8 was the entire chapter on similar polygons. We talked about similar triangles. Here we kind of just extend some of those concepts to similar right triangles, and specifically, kind of the second bullet point here. When we're talking about this altitude of a right triangle, what goes on there and how it breaks the triangles up and how we could find some of those lengths. So let's do it. So a very, very quick, this exact same slide came up in lesson 8.1 on similar polygons. So we're just recapping here. No reason to add it to our notes, but at least to mention when we're talking, whether it's triangles or any other type of polygon being similar, what are we talking about? We're saying that the angles are congruent. Okay, like corresponding, the matching angles are congruent, and then the corresponding side lengths not congruent but are proportional. All right, and we ended up using proportions to find a lot of unknown angle measures, or I'm sorry, unknown side lengths. So I was looking at angles here. So that's kind of what's at play behind everything that we're going to do today. Really, there's a very quick, short kind of note we're going to look at right here. So in your notebooks, let's get this set up. Altitude of a right triangle. We're going to start. I'm just going to kind of do it the way we would normally have done it in class. We'll start with a right triangle. I'm going to kind of draw it in a certain way here. That's pretty close there. Let's take that little extra piece off there. And I think we're pretty close to a right triangle. I can live with that. And let's call this triangle ABC. All right. So whatever, good old-fashioned right triangle. That's the name of the chapter, right triangles. So remember, altitudes going back a few chapters as well. The altitudes of a triangle is another way of saying the height of the triangle is really the segment that runs from vertex to the opposite side and hits the opposite side perpendicular, intersects it at a right angle. So you can see that two of my altitudes are actually the sides of the triangle. So if I put my pen on the vertex here and I say hit this other side here at a right angle, well, I would literally be following the side of the triangle until I hit here, boom, right angle. Same thing, if I start here, travel down, I hit the opposite side at a right angle. So that's nothing like, those are just the sides of the triangle. They're also technically the altitudes of this triangle. There's a third one though, and that's kind of the one we're going to look at, is if I put my pen on at point B and drop my altitude straight down and hit this side at a right angle. Let's call that point of intersection there point D. I've now divided this triangle up into, let's see, there's a small little triangle here, triangle BDC. There's a medium-sized triangle, BDA. And then, of course, we still have the regular, not the regular, but the original triangle ABC. So based on some of the principles we talked about in the previous chapter, these three triangles that we just mentioned all would be similar. Okay, so remember the AA similarity theorem, going back to last chapter, said in a triangle, if two of the three angles are congruent, of corresponding angles are congruent, then the triangles themselves would have to be similar. So let's just do a brief run through on all three of these triangles. Well, every single triangle that we have on this board right now has a right angle. All right, the little one has a 90 right here. We could extend it to this side if we wanted to, just to confirm, hey, triangle BDA is also a right triangle, and then the big triangle ABC is also a right triangle. So they all have a 90 degree. And if we kind of look at, let's focus maybe here on, color code it a little bit. Triangle BDA, I can see that it's got a right angle, and then it's got this angle A involved as one of its angle measures. Well, so does the big triangle ABC. So they've got right angle and they're sharing this. Remember, reflexive property is how we justify that, reflexive property of congruence. So the little purple one, ABD, and the big one are similar. And for the exact same reason, the fact that the little triangle over here, the blue one, triangle BDC, and the big triangle ABC are also sharing, there's the reflexive property going on with this angle. It's got a 90 and then angle C. These are also similar. So long story short, when this is all said and done, the three triangles that we see on the board here end up being all similar. All right. So what's going on here is basically, or the skill that kind of today this lesson boils down to is looking at these three triangles and being able to see all three of them in their own separate, non-overlapping ways. So what we could do here, what we'll end up doing is a lot of it, I think, involves just kind of spatially turning and rotating these. So if I said, I want you to tell me what are the three similar triangles here in this picture, I think it's made easiest um, if we can pull them apart and look at them all kind of facing the same way. So what I've done here, kind of while I was talking, I drew three triangles, a big, medium, and a small triangle, but I've situated them all so that the short leg was over here, the long leg was down here, and then the hypotenuse was right here. And if I can kind of in my head relabel this as like the big pink triangle here, triangle, let's see if I start here and travel from down the short leg from C to B to A, that would put the points C, B, and A right here. All right, so just see if you can follow this here. On this medium-sized triangle that I use purple to outline, if I travel down the short leg, I'd be traveling from B to D, so from B to D, and then over to A, that would put A right here. And then one more time on this, what I've colored in as kind of a blue triangle, if I travel down the short side from C to D, and then back around to B, I could hopefully very easily at this point, if I said, hey, what are the three similar triangles in this picture? If I just look here, it might be a little tough. I'm doing a lot of rotating in my head maybe and trying to get the vertices all lined up. But if I look over here at these pictures, I can just kind of go clockwise, counterclockwise, and just list my vertices in order. So I would say, for example, for a similarity statement, right, that's going back to last section. That this big triangle CBA, is similar to, let's go to the next one, triangle BDA, and I'm just kind of going in the same order, CBA, BDA, which would be similar to triangle CDB. And that's essentially the basis of this entire lesson. So every figure we see is going to look like this in some regard, whether it's rotated, reflected, whatever, but it's going to be a big triangle split into two smaller ones using the altitude, and we're going to use concepts of similar triangles from the previous lesson to find unknown side lengths. All right, that's it. We've essentially summed up the note. So here's from the textbook: the altitude is drawn, the hypotenuse, the right triangle. Two triangles formed are similar to the original triangle and to each other. That's it. Now, this is from the book, and I don't like this as much because it's pulled apart and they're situated the same way. I think it makes life a little easier on me, at least, if I do the rotating in my head and kind of always have these laid out the same way. I guess I'll leave it up to you to kind of decide. Let's take a look. The first example I have set up is essentially kind of doing the same thing here, so it'll give you a chance to practice it. Really what we have left are a couple examples of how we would use this to find unknown side lengths. All right. So pause it, draw the picture, what I'm asking it to do, and the homework is kind of set up in a way that I would ask you to draw those three triangles, identify the similar triangles in the diagram, essentially give me a statement of, not a statement, a similarity statement of these three triangles. All right, so here's how I would go through it. I would pull them all apart. I'm going to start with my model again, start with the big one. I'm over exaggerating where the long leg is, because the number one mistake that I see students make is that they draw pictures that look like this, and they confuse themselves about, let's see, is this my long leg up here? Yeah, it looks like my long leg. This one right here kind of looks like my long leg. This one looks like my short leg. And you, like I said, almost confuse yourselves, where I think if I start from the beginning with a good picture in that, and by good I mean it's It's very easy to see where my long and short legs are. I think I make my life pretty easy. So here's how I would do this. I would start, all right, let's start with the big one. I'm going F to G to H. F to G to H. So what I do, if you can kind of follow here, is I always just put my pen on the kind of the short leg, travel to the right angle, and then travel down the right, or I'm sorry, down the long leg. So on this medium-sized triangle, I went from G to J to H. G to J to H. One more time. Let's go on the small one. I'm going to travel from F to J to G. Perfect. F to J to G. With minimal work, I think I turned this into a really simple question of, okay, what are my three similar triangles? Well, let's start at the top here. Triangle, if I can read my own writing, that's an F. F, G, H would have to be similar to triangle GJH, which would also be similar to triangle FJG. So basically I'm just asking you to be careful and make sure as you list these here that these vertices all correspond, right? If I were to kind of pick, let's see, that this right angle J should line up with all the other right angles, so in this, on the medium-sized picture, J is the middle one. On the small one, J is also the right angle. On the big triangle, G is the right angle. So the middle letter should always be the right angle. Just for an example, I'm just kind of going through and saying how this should line up. Okay, so that's just, it's kind of a repeat of the skill we just looked at. Give you a chance to try it kind of on your own. The rest of the lesson involves using these concepts, similar triangles, to find unknown side lengths. So let's take a look here. I'll make this, I don't think this needs to be this big. You can see it. Let's see what we have going on here. So identify the similar triangles, then find the value of x. So you know what I'm going to do? Guess what? It gets a little bit, you're like, wow, is this really it? If you can figure this skill out here, and there is some skill to it, you think it's just drawing silly little right triangles, but there's some reason behind why we're doing certain things certain ways. Big, medium, small, very clear short leg, long leg. Let's rip through it here. Hopefully we can do it. I'm going to travel down the short leg to the right angle, finish on the long leg. So G to D to E. G to D to E. Let's do it for the medium triangle, which would be to D to F to E. D to F to E. And then on my small triangle, one last time, from G to F to D. From G to F to D. And I know I'm not putting the right angle symbols in here, but hopefully we can survive without those. All right, so this first part, now it's kind of the third time in a row of identify the similar triangles, no problem. Let's see, where can we squeeze this in? I don't want to take up too much, but we can do it over here, I think, by the figure. Triangle GDE is similar to triangle DFE, which is similar to triangle GFD. So I get to kind of finish just really easy copying down because we put in a little bit of effort to label those all out. Okay, so that's the first part. Identify the similar right triangles. This last part of finding the value of x, notice I'm not in a position where I can Pythagorean theorem this. I see people get stuck on a quiz or a test, and they're saying, well, can't I just figure out what GF is right here and figure out, like, I don't think we can, to be completely honest with you. There's not enough information to say, like, this GF is 4 and this is 6. I know they have to add up to 10, but I don't know what those are, and I don't have to find them. So there's no Pythagorean theorem option on the table right now. So here's what I would do. Let's look at the big triangle itself and use the numbers and just use those figures that I already have over here and just stick these values where they go. Let's see, the 10, right? 10 is the longest side up here. It's the hypotenuse. So I'm going to stick a 10 right here where the hypotenuse is. 6 must be the short leg because it's shorter than 8. So 6 is the short leg up here. So I'm going to put a 6 where it goes. And lastly, I've got the long leg. DE is 8. So I'm going to put 8 where it goes. I can use the vertices to guide me too. DE is 8. So DE better be 8. Let's do the same thing with this medium-sized one. What color do we use? Red. So if I focus on this figure right here, this triangle, DF, the short leg is X. And I know the hypotenuse DE is 8. So I'm using the vertices to guide me a little bit. I could actually find X right now, but let's at least finish kind of putting these on there. This one almost has an overabundance of information where I have a ton of info. They're not all like this. So let's see. On this one, I don't know GF, so I don't know the short leg. I do know the hypotenuse. DG is 6. And I also know the long, I'm looking for the long leg, which is X. Okay. So again, I'm taking a little bit of time. I already had the picture. It was just a matter of getting some of the numbers and the unknowns on there. All right, this should hopefully feel very familiar. We just came off a chapter where we were doing problems just like this. Find partners, find a match. And we're only ever going to work with 2 of the 3 triangles. We're never going to say like 10 matches with 8, matches with 6. That doesn't, how can I can't set up a proportion using 3 different figures. So we got to kind of follow the information. When I look at this, let's see, I see X right here. Let's see, let's use a different color. Let's use maybe this purple. I see this X. That's what we're looking for, right? It's got a partner here that I know. X partners with 6. So however you want to set it up, I could say X matches with 6 or 6 matches with X. Maybe I want to go top down. Let's do it that way. 6 matches with X. When I say matches with, I mean it's proportional to X the same way that this 10 is proportional with this 8. All right, so hopefully we remember setting up those proportions. I'm going to go short leg to short leg, like hypotenuse is to hypotenuse. 6 over X, like 10 over 8. So we end up not using this one, and that's okay. You know, it was there in case we needed it, but it's just an example of, all right, we don't need this one down here. I don't necessarily have to cross it out, but I also don't want you to be confused and saying, well, what happened to this third one? We just didn't need it. Let's solve for X. This should be hopefully a decent solve. 10 times X is 10X. We're cross multiplying. 6 times 8 is 48. I can handle that. We'll divide both sides by 10 and get X equals 4.8. All right, so that I'm assuming we can handle that part, the cross multiply part of it. It's the setup stuff I want to make sure everybody's on the same page with. All right. All right, we'll do a couple more. They all have that kind of that same feel to it. All right, so as I look here, let's do kind of the same thing. This picture, just to make sure we have enough workspace. What does it ask us to do? Find that. I should read the directions to do a better job. Find the value of y. Okay, write our answer in simplest radical form. So remember, that's just kind of code word for no decimals. We're not going to punch anything in on our calculator. And I'm guessing there's going to be a square root involved here, but we'll see. Let's do it. I'm going to go back to the same old. You get bored because it's like, well, I know how to do this. And when you get bored with something, it means you must know it pretty well. So there's my 3 generic triangles, big, medium, and small. If I want, you know what, there's definitely going to be people that start to kind of, do I have to have the vertices here? No, not necessarily. I could look at this big triangle and say, all right, you know what, the short leg here is y. The hypotenuse is 15. And we just don't know anything down here. So the long leg's unknown, and that's fine. We're just going to leave it. We'll just leave it totally blank right here, and that's fine. We don't need it. Let's look at the medium-sized triangle. I got to do a little rotating in my head. The short leg, unknown, don't know it. Okay, fine. Now I do know this. I could calculate it. It's not on the board right now, but 15 minus 4, this would be 11. So if I wanted to put that there, and maybe we should, I think it's not a bad idea for the long leg to put 11 here. But we also don't know the hypotenuse of that one either. So that's double unknown. Don't know it. So question here, don't know. So that triangle is a little bit limited with information. I don't have much there. Let's look at the small one. So on the small triangle, I know the short leg is 4 units long. I know, well, I don't know the long leg. That's that question mark. And we're looking for the hypotenuse, which I just covered up, but I still remember is we're calling y. So a lot less information on this one than the previous one. But here's kind of the cool part. Follow your information. Where do I have the most information? On this triangle and this triangle. And hopefully if we put the stuff where it goes, we should get some sort of line up going on. I'm going to go with short leg of this one and partner it with, hopefully we got something in that spot, the short leg of this one. So its partner is 4. Y partner is with 4. the same way that this 15 hypotenuse partners with this hypotenuse. So once I decide on my triangles, I can't jump around. I can't, like, I wouldn't, even if we knew a number here, I couldn't like match it with this 11. You decide on two triangles, stick with those two triangles. This one doesn't help me at all just because we didn't have enough information. So slightly different solve on this one. Let's start with the y times y. What the heck is y times y? Not 2y, but y squared. Oh. And then 4 times 15 is 60. All right, so we've been in this spot a few times this chapter already. If I were to square root both sides, that's how we would finish this and solve for y. Y is equal to, remember, we're not picking up the calculator because it said simplest radical form. We're just kind of saying y is equal to the square root of 60. So recall from lesson 9.1, how did we fix that? I need to break this 60 up into two numbers that multiply to 60. I want one of them to be a perfect square, and it's kind of convenient the way it works out. It was the original two numbers that we multiplied, right? This 4 and this 15. So this one, it's kind of just coincidence. That's the way it worked out. 60 actually does have a fair amount of factors, but 4 and 15, I think, is the combination. Remember how to finish it. That we do the square root of 4, which is 2. The square root of 15 is just the square root of 15. I don't know what that one is. And that ends up being our value for y. Y is equal to 2 times the square root of 15. Oh, there we go. Kind of weird. Nah, that's not true. Same process that we did on the previous one. Guess what we're going to do on the next 4? And we'll try to go quicker here just to kind of make sure that we keep the video to a manageable time. But also, we're going to see a few things that we haven't quite seen yet. All right, let's keep her moving. What do we got here? Find the value of x, express your answer both as a simplified radical and round to the nearest tenth. So we'll get the calculator out here. I'll have to dig one up, and we'll see what we got. So I kind of left a little bit of space here for my triangles. I think we can squeeze both of these in here. I'm just trying to give us some different looks, but I'm also trying to illustrate that no matter what the original problem looks like, how does my setup start? It always starts with those same 3 generic triangles: big, medium, and small, long leg, short leg, hypotenuse. Let's see, where's my big triangle right here? So my hypotenuse, this one's kind of tricky, I think. Hypotenuse is 20, right? So I'm putting the 9 and the 11 together to say 20. And what I think about this one is kind of tough to tell. Is this x, is this the long leg? Or is this the long leg here, or is this the short leg? And I guess you can, if you look at it close enough, you can probably guess that this one's longer. So this would be the short leg x here. But without having to guess, do I know for sure? Like maybe it's just a crummy picture. This actually does have to be the short leg because it's part of this smaller triangle that has a 9 for a side length here. So I can still use these numbers to help me. The fact that this number 9 is smaller than this 11 means that this is the smaller triangle. So maybe that's something you can do too. Small versus medium, something like that. Just something to think about. All right, let's go to that medium triangle. So the medium triangle is right here. So it's kind of that we got to decide, where does this 11 go? Is this the long leg or the short leg? And because the 11 is in a spot where the short leg of the medium triangle is always going to be the long leg of the small triangle. This 11 has to be my long leg. So I think we're going to wind up with kind of a miss. Like we don't have enough information on this one. Because if we look at the small triangle, that's where my information is. My hypotenuse is x, and my short leg is 9. So kind of tough. When the triangles get kind of close in size, it can be kind of tricky to tell like what goes with what. So use the numbers to guide you a little bit. Use little s, little m to kind of remind you. But I think if we did this right, we should get that same lineup. X. Let's see if we can solve it up here. X partners with 9. The same way that 20 partners with x. So it's going to be kind of a same type of finish here. I'm going to get with an x squared on the cross multiply. 9 times 20 is 180. Kind of a bigger number there. Any perfect squares that go into 180? I know 36 goes in there. 180 divided by 36 is 5. So I think that's the combination we're looking for. Let's see. Before I start writing my solution here, let's do it the right way. Let's break this 180 up into 36 and 5. Remember, we keep them both under a square root until we're ready to do the one that we can do. Which one of these can we do? You can, 36. Square root of 36 is 6. The square root of 5 just stays put. So there's my answer as far as the value of x in simplest radical form. It did ask, I don't want to forget, it was asking for a round, I think it said to the nearest 10. So I literally just have to go 6 times the square root of 5. It's just getting some practice using the calculator and the square root function. About 13.4 is where we end up there. So I like that one, partly because of just kind of how the figure looks, and it's a little bit tougher to tell. All right, 3 more to go. 1, 2, 3. And like I said, they all have just slight variances, so make sure you don't check out early or miss something here. All right, you know what the setup's going to be. Big triangle, medium triangle. I'm trying to cram them in a little bit tighter just because we're going to need a little bit of space to solve here. Let's do it. Where's the big triangle? Let's see. Big triangle, don't know. Oh, there's my hypotenuse. This is kind of weird. Let's call our hypotenuse x plus 8, because that's the full length there, right? All the way from here to here is x plus 8. All right, so we're a little bit limited on that one. Maybe we get some more information here. So on my medium-sized triangle, I know this short leg is 12, and we know the long leg is x. Now I wrote all this stuff in here, and I feel like I'm confusing myself. This was x, and that was 8. Okay, yep. And let's go to the small triangle. What do we know? We know the short leg is 8. We know the long leg is 12. Oh, I like this one. This one will be okay. Let's partner them up. Use my orange. That's what I've been using. 12 partners with 8. The same way that x partners with 12. Cool. So this is one, when we start talking simplest radical form, this cross multiply is just 8x. 12 times 12 is 144. We don't end up with that. So to put this in simplest radical form, there's not really a square root option. Why would I square root? There's no square root, doesn't come up as far as solving this. So I just need to divide both sides by 8, and I get x equals 18. Remember, we said earlier on that is considered simplest radical form. It's a number rounded to the nearest 10th. Technically, you could call it 18.0 to be super technical, but on a whole number finish like that, yeah, I think we've covered both types of solutions. Okay, cool, great. 2 more, let's do it. Stay with me, same directions. I just kind of split it here to give us some room to work. Simplest radical form and 10th. Let's do it. All right, see, it's got a slight wrinkle here. We're getting this same setup. Same 3 generic pictures. Let's see, big triangle, what do I know? Nothing, but I do know the hypotenuse is 20. Okay, let's go medium-sized triangle. I know I'm looking for x. I know 15 on the long leg. Nothing on the hypotenuse, though. Now, this one looks like we're short information, right? It's like, don't know, but I do know long leg is x. Here's kind of the hang up on this one, and hopefully it's something that's not too big of a reach. We know this distance right here, right? If this full length is 20 and this part's 15, we all know that this would have to be 5 right there. So my short leg, we should say, is 5. So a little piece of like missing information that we had to add there, but you can kind of see it's worked out every time where we end up. Yeah, this triangle doesn't have much information, but I'm able to partner up x with 5. The same way that this 15 partners up with this x. So we've seen this finish a few different times. X times x going this way, x squared. 5 times 15 is 75. Great. We can square root both sides. X is equal. I've done that twice now. Let's break the 75 up. Right, so let's see. There's a 25 tucked in there. 25 times 3. So I think we can finish it here. X equals, what's the square root of 25? 5. What's the square root of 3? 3. Awesome. And not forgetting that it did ask to do it to the nearest tenth. So 5 times the square root of 3. 8.7 if we round accurately. About 8.7 to the nearest tenth. All right. Ooh, I like part D here. It's a good one to finish with. Hopefully, I didn't say it earlier. I usually try to remind you, make sure you're pausing them, trying them. It's all well and good to copy me as I do it, and there's nothing wrong with that the first time seeing it, but this is our, let's see, 1, 2, 3. Oh, no, 1, 2, 3, 4, 5. This is our 6th one doing it. I would hope by this point you're feeling at least comfortable enough to kind of get things started and try it before we go through the solution. So here's our solution. This still got time to pause it. You know how I'm going to start it. I got my 3 triangles. Let's see. Big triangle. Hypotenuse is 12. Short leg is 6. So right there, it's already telling me, like, I'm betting we're using this triangle. It's got 2 pieces of information. They're both numbers. If I needed to, could I find this side here with, sure, like, right, 6 squared plus unknown squared equals 12 squared. So don't forget about the Pythagorean theorem. I know we get so wrapped up in this new method that had it come down to it, if there was an x right here and it said find x, well, I'm not going to maybe mess with the 3 triangles. I'm going to go x squared plus 6 squared equals 12 squared. So don't lose sight of that. Sometimes I'm guilty of that as well. So I know it's not asking for that, but just wanted to at least mention it. Like, if we can use other methods and it doesn't, the directions of a quiz or a test or a homework isn't saying, hey, you can't use Pythagorean theorem, go ahead and use it. All right, let's go medium-sized triangle. We saw it a little bit today where it's like, okay, I don't know the hypotenuse. I don't know this short leg. Could I come up with an expression for the long leg? Sure. It's 12 minus a. But being that that's the only piece of information we have there, I'm probably thinking that this triangle is not going to help us too much. And actually, as I'm looking at this bottom one, I'm kind of guilty of, I don't think that was a great picture. I want to make sure that I'm able to look at this and see my long leg on the bottom. So anyways, let's go to this, the small triangle. I know the short leg is A, and I know my hypotenuse is 6. And one last time, very, very conveniently, we get everything to line up. This 6 partners up with that A, the same way that this 12 partners up with this 6. And it's one of those really nice ones that finishes, let's see, let's go this way first. 12 times A is 12A. Going the other way, 6 times 6 is 36. So yeah, look at that. Divide both sides by 12. It even works out to a great number. A equals 3. So hopefully, like I said, after now, what is that, our 6th one we said, a 6th example? That's pretty much what the lesson is using those 3 similar triangles. Is it a little bit of work and setup? Sure. But I think it takes kind of the guesswork out of it. I've seen people try to do some weird stuff and create new variables, and you don't have to do that. Stick with the 3 triangle method and you'll be in really good shape. So that's it. That's lesson 9.3. We definitely hit similar right triangles, the altitude length. We found a bunch of other side lengths. We should be good. Let's call it there. 9.3 in the books. I will see you in future lessons.